MySQL or Oracle. Um, and this talk is going to focus on given us query, how is it going to execute it, and give you back the results. Couple of minutes, sorry. So let's get started with a little bit of history. There was this project called System R from the IBM in early 1970s, and it was the first implementation of databases. So it was proprietary, and a group, collection of college students, a group of college students in University of California, Berkeley, started writing a database inspired from System R called Ingress, and they had partial success with it. They had a lot of problems with it, and they started to rewrite it from scratch, taking the good parts of it, and they implemented a system called Postgres. It used a query language called PostgreSQL. It's somewhat similar to SQL, and it was released in early 1989, and then it was kind of idle after that for a few years, and then open source community adopted that database, and they added the SQL support for it, and they called it PostgreSQL. Still, a lot of people used to call it Postgres, even now as well. It was released in 1996, and it's nicknamed as one of the world's most advanced open source database. So why Postgres? So it has a very good OLTP system using MVCC, which is tested across billions of installations, and it simply works at high transactions. The other reason is it has a lot of data types, extensions, and features built in. A lot of people used to joke Postgres as Emacs of the databases because of the availability of plugins for Emacs. The other reason why I personally like Postgres is because of the community support it has and documentation. Moreover, it's moving on towards path of being framework instead of just yet another RDBMS system. There are lots of organizations adopting this code base and using it as a framework to build their own database systems. Redshift, Greenplum, Citus Data, etc. Okay, let's get started with the architecture. So similar to all RDBMS system, this Postgres is also a client-server model. We will have the Postgres server, which will respond to clients' queries, and we have n number of Postgres clients, which just connects to Postgres server using some kind of API. I will talk about that, and it hands over the query to the server. It's going to do some operations, give you back the result set, and the operation terminates. That's a simple architecture, typical server client model. So what happens under the hood in the connection initialization stage? So we have this client application. It can be any Java application, Rails application, anything of that sort, or simple pSQL, which is the command line which we use to connect to Postgres. When this client instantiates, it's going to use an underhood library called libpq in the native systems like Rails, Python, etc. Of course, JDBC, for Java applications, JDBC has its own implementation of this layer, and that is the Postgres JDBC driver, by the way. So when the client application instantiates, it's going to make use of this libpq library to send a connection to Postmaster, which is the real Postgres backend, which does admin activities in the sense creating a new connection, destroying a connection, doing a vacuum, instantiating a vacuum, etc. So we have a new application. When we run the application, it's going to have libpq to send a request to the Postmaster, and then Before getting started, let's just execute a simple query in Postgres before that would help us to have a better understanding. So how do I start Postgres? And so this is how I start Postgres. Is it visible at the end? Yeah, Postgres is up and ready to accept new connections. Now let's try to connect to this postmaster. Okay, now we are connected to Postgres, and we can simply do /l, which will give the list of databases we have, and we can simply connect to a database and execute a query. I'm connecting to a database called foo, and then I'm just executing a query here. Yeah, just similar to all other databases. So what just happened? We have this command called psql-new Postgres. psql is the command line. psql is the command line client. It's going to create a new connection, and once a connection is established, what happens here is, okay, now a postmaster got a connection. It's going to fork a new process called Postgres backend. The necessity for this is to exploit concurrency. So let's say we have 8 CPU cores, which means at that point in time I can execute at least 8 threads in parallel. Postgres kind of uses this to advantage. So whenever I get a new query, whenever I get a new connection, I'm going to fork a process which is going to run on a different CPU. And then postmaster goes off from the loop. No other communication is with postmaster. libpq will directly send the query to the Postgres backend, and then Postgres backend will execute that query and give you back the result set to libpq. And that's about it. So in this process, after this result set is given to libpq, and if there are no other further queries that needs to be processed, and if the client instantiates a disconnect, it's going to send a disconnect signal to postmaster, which is going to kill off this Postgres backend. So little bit in detail. So this is what happens, right? We have this postmaster daemon process, which is the root of all the processes. And when a new query comes in, it's going to spawn a new server process for each and every connection. It's not for query, it's for each and every unique connection. And this backend is going to be given the query. There is a shared memory layer which is being shared by postmaster as well as Postgres. This is where all the work in progress data and everything else, basically the buffers is kept, and it's going to be shared across all the Postgres process. Basically, there are two kinds of buffers: shared disk buffers and shared tables. We will deal with more detail later. And then we have this kernel disk buffers and then disk storage. This part is taken care by your operating system. So if it's going to be Linux, there is a file system cache layer, which is kernel disk buffers here, and then of course the disk storage based on your storage needs. So if there are any questions, please feel free to stop me because everything is going to be built upon these models. Okay, I think it may not be visible at the back, but I'll just walk through it. So any program, any executable will start the main. We have the main at the top, and then postmaster here, and then lot of Postgres process. what each and every Postgres process does for a query is mentioned in this block. Um, so when it gets a query, right, it needs to parse the query first to figure out what that query actually meant to the system. So it uses X and LOC, Yak and Lex, I'm sorry, which is one of the best parsing tools out there. And so the input to that parser is going to be the query itself. Output from the parser, it's going to be a data structure called parse tree. It's just, you can think of it as an abstract syntax tree, and that output is going to be the input to there's something called traffic cop, and then utility commands. Traffic cop basically understands your parse tree to figure out what the user wants. Does he want to create a new table, a new database, or does he want to do a select operation, insert operation, or anything of that sort? And based on the operation, it's going to route the path that the query processing will take. If it's just going to be a select query, it's going to choose this path. If it is going to be, let's say, utility command like vacuum or drop table or create database, it's going to create the utility path. Utility path has a separate set of shared libraries which will implement that using internal data structures of Postgres. So the rest of the commands, right, select, insert, etc., will go through this path where the abstract syntax tree or query parse tree is going to be fed into a rewriter. So what happens in the rewriter is it will take in that parse tree and transform it to another parse tree based on the rules we have defined in Postgres. For example, if we have a view and the select is on a view, it's going to rewrite that query to the parent table. So these kinds of rewriting is done in the rewriting phase, and it's highly customizable. You can put in your own rewriting rules as well. This rewritten parse tree is going to be given to the next stage where paths are generated. Path in the sense, how should I execute this query? Given a parse tree, it walks through that parse tree and comes up with n number of combinations by which I can execute that parse tree. So it is not going to be at detail, it just approximates things and comes up with a cost for each and every manner in which it will evaluate that parse tree. And it's going to select an optimal path. That is the output of the generate paths phase. The next phase is going to be generate plan. So it's going to take this generate path and add in more details to it. Like this is where the data is in the disk, this is where the data is in the shared buffers, and this is the operation you need to do. It's going to add lot of details into that generated path and agent a physical plan, output a physical plan that is going to be used by the executor to actually execute that physical plan. There are actually a lot of other tools that come into play here. We have the storage managers, catalogs, utilities, and all those things. Catalogs are group of tables in Postgres which records system level information, like how many rows are present in this table, what are all the indexes we have, and what are all the tables present in this database. These kinds of information are recorded in catalogs. Any questions?
How is it able to arrive in execution path? See, any database after you give your SQL, it does a parse and it creates a map based on whatever query you have passed, right? Based on that map, it has to arrive on multiple execution channels or the execution path which it has to. How is it?
So let's say that I'm going to do a select star from users where username is Varadarajan, right? Simple query. How can I execute this query? I can use an index if it is there. I can do a sequential scan if there is no index. I can use some caching libraries. Let's say you have your own rule engine and you have written a caching library. I can use that cache to come up with the data. So we we just now came up with 3 plans, right? I can use the index, I can do a sequential scan row by row in the table, or I can use a custom library which caches it. So out of these 3 parts, it just figures out which one is the optimum using the cost. But how does it come up with these 3 parts is an input to the generate part phase. This catalog, right? This catalog has all those informations. Like this table has an index. So if it has an index, can I use this index to generate a plan? It's all going to be written in your rule engine, basically.
So that rule engine you are saying it is a configurable or it is a
So Postgres currently is moving towards the idea of being a framework, not a hard coded database, which means you can literally replace any part of it. There are ways to check out the existing query generator. The existing query generator is called Gecko, genetically optimized query, genetically engineered query optimizer. But you can just remove that optimizer and put in your own optimizer. But you will have to recompile it. Yeah, basically. Okay, let's look at an example. So in this query, select star from tab 1, tab 2. It's a cross join, by the way, and where tab 1.a is equal to tab 2.f, which transforms it to an inner join. So this query is going to be fed into the parser, and the output of this query is going to be a parse tree like this. So this simple query has 3 phases, right? Target list, join tree, and qualification. Target list is just going to be all columns from both the tables, tab 1.a, b, c, etc. Join tree, it's going to be a cross join between tab 1 and tab 2. And then we have the qualification, which maps to an operator node, data type, which is integer here. And then the operation for qualification is tab 1.a is equal to tab 2.f. So this is how parse tree gets represented from the basic query plan. And then that parse tree is going to be fed into the rewriter, and that's the rewrite rule saying that, oh, tape 2 is not a table, real table, it's a view. That is further expanded using that query. And this is going to be another tree with all those data. And this rewriter recursively generates this rule until all the nodes are the terminal nodes. Okay, now we have the output of rewriter. I'm going to skip the optimization part, and I'm going to give that to the executor, because the rewriter itself can be transformed into a lazy plan by the executor. There is no need for optimizer for the native installation of Postgres. You can have it as an option one. So in the executor phase, there's going to be the executor phase is actually implemented as a demand pull pipeline. If we have worked with functional programming, you can think of it as lazy evaluation of list. There are basically 2 nodes, primitive and materialize. So probably we should hold on to this because we will deal that in detail in the next few slides. Let's take an example of this query, right? Select sum of sales from weekly sales where year week equal to 2014-01. So output for the first stage scan.l, which is the lex, will break this query into words or tokens, and then that's going to be passed through the second stage of the parsing, which is yak, and that's going to give you the tree. This is how a tree looks like. So in the initial phases of the tree, we have a lot of attributes here that specifies or describes the query, and one of the attributes that we should be interested in is in the rel ID, relation ID. So relation ID for this is 6464497, right? Where is this information stored? It's going to be stored in the PG catalog, as we saw before. So if you do a select rel ID from PG stat all tables where rel name equal to weekly sales, we get the same rel ID as well. So it's kind of PG catalog is kind of the metadata table which has more information, and all other places will have an ID pointing to those catalog tables. And then in this query, we are interested in these columns called year, week, and sales. Year, week for qualification and sales for aggregation. And if there are any aliases, it's also mentioned here. And most important one to note is command type 1. So if you look at the definition of command type, command select, which has the enum1. So this is the first stage of the parse. I mean, this is one part of the parse tree. The other part of this parse tree is the join statement. So if you look at the initial query, right, there is no join in this. But what Postgres does, based on the optimizations, is to possibly pull it up as a join operation, and that is what we get here. And you can see that first one is going to be a variable, and the second argument is going to be a constant. So it kind of pulls up the where condition to make a join because it's optimized to do that. And operation number 66, as mentioned in the quals section of the tree, points to equal. Okay, now we have seen the qualifications and the select section. What about the aggregation? Aggregation is also a part of the parse tree, and it's going to be part of the target list tree. Let's say select star from PG aggregate where AGGFNO ID is 2114, which is mentioned here, and that is going to be pgcatalog.sum or numeric add. So it's kind of all the configurations are present in the catalog tables. You can add your own operations, you can do things, you can customize it to a greater extent. So yeah, so now we have this query, and if we do an explain analyze, this is what we get. A query plan, right? Now how are we going to execute this query? It all works like this, right? So at the end of this query, select sum of sales from weekly sales X where year week equal to this. The expectation of this query is to give a sum of sales, which is going to be the topmost node in the tree, and that is going to be the additive buffer. I'm just going to call it buffer because you need some place to do the arithmetic and keep the values in. Now, in order for that, let's think of this case as a client, for instance. This is the client application. Now, I'm going to call that operation, and the root of that query is going to be the sum of sales, which is the sum execution node. What it does is it asks to its children the first row it has, which means if I have two rows qualifying that condition of where check, it's just going to ask the first row, or it's just going to ask the first row, which in turn the sequence scan, let's say, it's going to ask the storage manager for the first row, and it's going to give a first row, and then it's going to filter. Let's say if year week is for the first row, year week is 2013-52. It's not going to give that row to sum because filter fails there. It's going to get the next row, let's say it has year week 2014-01. It's going to pass that row up towards the sum, and that is where it's going to compute and store the temporary values. This iteration happens until scan informs sum that I don't have any more rows with me. And how does it know? It in turn asks the list of pages of storage buffer, and storage buffer will say that, oh, I'm done, there are no more rows with me. So it's kind of lazy evaluation, and it bubbles from the bottom to the top. That is why when you do a select star from, let's say, table foo, limit 10, you will get faster results compared to that same query without a limit, because the topmost node will stop right after getting the 10th row. So are there any questions till now?
evaluation for each and everything, right? One, like a lazy evaluation, you take one, evaluate, put it up, then take one again. How does it perform in case of a batch operation where I have to read the whole thing? Doesn't that kind of make a lot of reads or a lot of cache hits again and again?
Yes. So there are two kinds of applications, right? OLTP and OLAP. Okay, sorry. The question is, doesn't this streaming model degrade the performance in the when we deal with batch operations? The answer to that is there are two kinds of systems, OLTP and OLAP. OLTP predominantly deals with minimum set of rows. Transactions to put it. OLAP deals with all these ETL kind of batch jobs and other things. The idea behind coming up with this query executor is we should focus on OLTP. And if you need to execute batch operations, you have the flexibility to throw this executor out and write your own executor. And there are extensions where you can write your own executors and hook it up to the execution engine. There are a lot of interesting projects there is this thing called SIMD, single instruction multiple data, wherein you can add 4 numbers, let's say 4 integers at the same time based on the CPU instructions. So those kind of execution plans will be very good for OLAP-like solutions. And there are implementations or there are extensions to put it the Postgres way to do that. You just have to install it and run it.
The execution plan at times also changes based on the data that is there.
Yes.
It has to know based on statistics how much data, whether to use the index or not use the index. So where exactly is that?
Okay, that actually comes in the generate path phase. So there's a slight problem to that, right? So the way databases work is, let's say you have a table with 1 million rows, and the way to figure that out, figure the cost for each and every plan is based on a sample of rows from the table. Postgres has a scheduler which will frequently scan the tables to figure out the statistics. It randomly samples around, let's say, 1,000 rows, and then comes with a metric like, oh, for this column, this seems to be like a binary column where gender is either male or female. There are only 2 values for this. And the ratio of these 2 fields is like, let's say, for 2 rows of male, there is 1 female row. These kind of statistics are derived by the Postgres statistics collector and kept it in a table. After coming up with a lot of plans, it is going to use this statistics to see which one has the lowest cost, least cost. The problem with that is your sample itself might not correspond to the original data set present. It can simply sample first 1,000 rows and say that, this column is somewhat skewed, and use of index will not give any result. But actually, that might not be the case because of the sample size. It takes some time to come up with a good sample. We will have to try and experiment it. And to make it even worse, it's a genetically engineered query optimizer, which means we have no control over how the query is being framed. At frequent intervals, we have to run this command called vacuum full verbose analyze. You can take the verbose part, vacuum full analyze. What this does is, this is going to garbage collect your table and then collect fresh statistics. The reason for doing this is present in the forthcoming slides.
Actually, this Oracle is having the cost-based rules and also rule-based index, right?
Yes.
So, if anything, can be able to say this is a rule, you have to execute this way or that
Yeah.
way.
So, if you you can say a lot of settings here. How does how long does it take, or how much does it cost to do a sequential scan? How much does it cost to do a random page retrieval? How much does CPU tuple execution cost? These are all the costs that Oracle gives you as well. This is kind of given at the Postgres cluster level, but you can override it at runtime as well. Moving on. Now we know how query got executed, and let's learn about how transactions are done in Postgres. So transaction, as we all know, is an atomic unit of work. I don't think it needs any more definitions or examples. And the four most basic properties of transactions are asset properties, atomicity, consistency, isolation, and durability. Any transaction or the system database system should guarantee all these four things. So let's take an example. We have two functions here. One is the transfer function, and the other one is the report sum function. Transfer function transfers date, let's say 50 rupees from A to B, and this is how it is implemented. Read balance of A, subtract 50 from it, and write to balance of A. Similarly, read balance of B, add 50 to it, and write it to B. We have another function here called report sum. It's going to read the balance of both A and B and then add it and print it. Let's say these are the two functions we are going to deal with, and atomicity means either all of these commands commit together or abort together. So let's say it executed till here and there's an error here, then it shouldn't leave at that state. It should roll back all the operations that it did before it. That is the atomicity. And consistency is by rules: not null, unique key, foreign key, length, etc. We all know this. Isolation. So one transaction should not affect the other transaction. Let's say this, right? I'm going to execute the transfer method first, and then I'm going to execute the report sum first. This does not cause any issue, and this is consistent. But how about this? First, we read the value of A and subtract it, and suddenly there's another transaction that's going to come in and do a report of sum, which will give you the wrong value because we just lost 50 rupees from this, but it was never added to B. This is inconsistent. Durability. So we will actually see how isolation is done in a while. Durability means once you have committed a transaction, it should be visible to others based on the isolation level, and there should be a guarantee that it should survive server failures. So from this we can see that ideal setup is going to be serial execution and disk sync after each and every transaction, which is going to guarantee it to an extent. But yeah, you can have cache in the disk layers, which gives us more problems. But this is what you will have for an ideal setup. But this is going to be very slow. If you're going to have millions of transactions, this won't scale. So how does Postgres solve this? So for solving asset properties, Postgres makes use of two concepts. Basically, one is called MVCC, multi-version concurrency control, and the other one is called VAL, write-ahead log. Constraints, yeah, we all know that. Multi-version concurrency control means, so if I have to execute transactions concurrently, I need to come up with a mechanism. Do I do locks, or can I use something more smarter? Of course, you need to lock, but to what extent is the question. Now, Postgres uses this thing called multi-version concurrency control, where the concept is only write blocks writes. None of the other things actually block any other things. The way it is executed is, it has multiple versions of the same row. So when you create a connection, it's going to give you a version, and the changes you do to that is to you and not to others. When you do a commit, it's going to merge it back to the main line. That is what multi-version concurrency control is all about. You can think of it like a Git branch or something of that sort. And the other thing that is inspired from functional programming is immutability. In the sense, none of the data actually changes. It's always going to be immutable. Only the metadata of the row changes. None of the data, even updates and deletes, does not delete the metadata. Does not delete the data. It just changes the metadata. This means we are going to generate a lot of garbage, and we need a garbage collector to free up all the disk. You can think of it like a JVM garbage collector, and that is what vacuum is all about. So if you do a lot of inserts or updates or deletes, it's going to create a lot of garbage data, and it needs to be garbage collected, and that is what vacuum does. When you do a vacuum, statistic basically changes, and that is what you need to run vacuum full analyze. It can be triggered manually, or it can be an auto trigger as well.
Sorry to interrupt you. So in the previous slide, you said that write blocks, right?
Yeah.
So consider a scenario where there is another process which is selecting a data. In such kind of things, right? If write blocks from only writes, the data will be not get the correct data in the read, isn't it?
We will actually go through a demo. Can you hold to that scenario for a while? Okay. Just to get more information, each and every transaction is given a transaction ID, and Postgres records two fields for each and every row present in the database. That is going to be xmin and xmax. Any transaction ID greater than xmin is going to see that row. Any transactions with less than xmax is also going to see the row. It's basically the range at which that transaction is going to be seeing that row. So each and every row will have these two fields, and let's actually talk about isolation levels before going to the demo. There are 4 isolation levels in databases: read uncommitted, read committed, read repeatable, and serializable. Read uncommitted means you can see the changes that is made without even issuing a commit in the other transactions, which means you can still view the changes that the other transaction makes without even that committing the data. It's really bad for a transaction system. It's not implemented in Postgres. Read committed. There are 3 levels of noisiness in the data we read. One is dirty read, which means you can read uncommitted data. Non-repeatable read means in a pointed query, like let's say select star from users where username is equal to Varadarajan. This table, this row, the row written by this query is guaranteed to be the same even if you execute this query again within the same transaction. That is repeatable read, and the opposite of that is non-repeatable read. Phantom read is the non-repeatable read version over ranges. Let's say select star from year week, let's say select star from sales, where year week between 2014-01 to 2015-01. The number of rows returned for this query might differ during the stages of transactions. So that is phantom read. So in this 4 levels, read committed is going to give you non-repeatable read and phantom read. Repeatable read is going to give you just phantom read, and serializable, which means only one executor is there, is going to give you good quality data, nothing of phantom read or non-repeatable data or anything of that sort. Postgres implements only 2 of these, and that's going to be read committed and serializable. Let's look at a demo. Okay, let's look at few scenarios, right? First scenario is going to be, is it visible? First scenario is going to be, there are 2 transactions, one is going to write and the other one is going to read. Before even getting started with that scenario, let's clear the basics. So this table has only one column called ID for simplicity, and let's do this, right? Let's create a transaction here. Let's start a transaction here, insert some value, and then see whether it's visible to other transaction without being committed or not. So this is going to be the first transaction. You can see that ID of that transaction is going to be 223920, and this is going to be the second transaction. ID of this transaction is 223921, which means this is younger than that. I'm sorry, this is the older version than that. And let's do an insert in this. Okay, if you do an insert here, and if you do a select xmin xmax start from x, you don't get any rows because this is not yet committed. But if you try to execute that same query here, you can see how it works. You can see that xmin for that row is set to 223920, and any transaction ID with ID greater than this xmin, which is 223920, can see it provided this row is committed. Let's do a commit here. Now the condition applies, and we can see that row there. So this is the basic scenario, and updates works in a similar manner as well. Let's see an update. Okay, now we updated a value, but I haven't committed it. But if you look at the table, if you do a select xmin xmax star from here, you can see the old value here, but that value has a max ID, xmax, which means a transaction which is less than that xmax can read that row. And once this is going to be committed, that row will go off. So it's all based on yeah. So it's all based on few set of if else logic, all with xmin and xmax. So all this MVCC is implemented using if logic using xmin and xmax. That's the simplest way I can put it. And there are complex scenarios which does exist. For example, this is good for reads. What about dependent writes? Let's take an example of dependent write. I'm going to insert a value first, a sample row into the table. And after inserting this, I'm going to start two transactions, and we are going to modify the same row in both the transactions. You can see that it blocks. After the first write, it's going to block until that transaction completes. If you do a commit here, it's going to say it has updated 0 rows because it serializes if there is a lock and the first one succeeds before the second one. And what if you want to resolve this conflict manually? What you need to do that is to deal with something called serializable. What you can do is we will repeat the same scenario. Okay, the first one succeeded. How about the second transaction? If I'm going to do an update to, let's say, it's going to block again. But what happens if you do a commit here? It's going to allow the application to take care of the conflict resolution. That is what basically serializable does. Either you can ask Postgres to resolve itself with the read committed isolation level, or you can specify an isolation level here, one of the hosts, but Postgres has only two, and that's going to be serializable or read committed. If it is serializable, it's going to throw out an error, and it's up to the application to handle the error or conflict resolution. And if it's going to be read committed, it's going to try to play back the same query once the lock after the dependent write is unlocked or relieved. So that's how MVCC works basically. Any questions before we move on? Okay. Still have a couple of slides. This one is going to be about write-ahead logging. And so this is the last part of the asset properties, which ensures durability. And the objective of this is okay, I'm going to do an update on a big table. How am I going to do this update? Should I do that directly to the rows, or can I record it somewhere, let's say in a log file or a journal, you may call it, and then continue with the execution? So Postgres does this thing called write-ahead logging. Once a query is given to Postgres, it's going to make a note of that query in the log files and all the data and other things, and it's going to fetch all the data that is required to be processed by the query into shared buffers, which you could think of as a RAM memory, and it's going to change the shared buffers and leave it at that stage. It's not going to push those changes to disk. It's going to leave it like that, but it will write to the val file and sync that val file for each and every commit. Since val file is a sequential file, it's going to be very fast. Committing it takes less than milliseconds, and this path. So this path is going to be very, very fast, but this is going to be somewhat slow. Modifying shared buffers is going to be slightly fast. So this completes first. Shared buffers are modified. It's not flushed to disk, and response is returned to the users. At periodic intervals called checkpoint time, it's going to flush this to disk. And that is the reason why things might be faster in databases where write-ahead logging is involved. So I'm just going to skip these things because of lack of time. And this checkpointing, which merge the changed shared buffers with the disk, can be triggered using two fields, which is timeout or size. Once a checkpoint is of this size, I will basically merge it with the disk, or I will just keep it in the memory. So what are the other uses for write-ahead logging? Training replication and point-in-time recovery. You can say that roll back my database to, let's say, 2 days before and to this time, and you can still find out the exact rows you have. So that's about the transactions part. Probably will stop here. Are there any questions?
Does it come under open source?
Yes, Postgres is called as one of the most advanced open source database available. It is full of open source software.
Any metrics to compare it against this Oracle SQL, the commercial database?
So you do have commercial support available for Postgres as well. There are a few companies that give you that. Like Enterprise DB, and now Citus Data has its own big data analytic versions of Postgres with their own storage engine and other things. You can get support, and I think most of the features that is needed for an RDBMS is implemented in Postgres. There are a lot of applications being moved on to Postgres because it's open source and the community is very good.
What is the maximum size it can handle?
There are benchmarks where this database gave a few millisecond responses for more than 400 billion rows on the internet. Yeah, Skype uses Postgres basically.
I never used Postgres. I never use Postgres, but I use MySQL. Why I need to select Postgres if I want to use future?
Okay, MySQL, it's called most popular database. So the reason for that is it takes relatively less effort to get it up and running. But if you compare the amount of options you have to that of Postgres in terms of data types or extensions, Postgres has far more extensions. And one other advantage I see with MySQL was the extensibility of MySQL, which Postgres is currently adapting to. That is why I mentioned it's called it's going towards framework. But major reason why people are moving towards Postgres, it's because Oracle is going to control MySQL. And so if you are reading Hacker News, you might see that there's a bug that has been around for nearly 10 years and it hasn't been fixed because the solution is proprietary.
Also, MySQL doesn't support check constraints, whereas the PostgreSQL it supports check constraints. In MySQL, using want to use some check constraints, will be doing an application level, right? So, but this Postgres SQL almost similar to popular databases. So, it allows you to do check constraints, which is a basic requirement in all DBs.
The primary reason is, as he said, because Oracle is taking control.
Yeah. That is one of the major reasons. But interestingly, big data companies like Twitter, Facebook are still using MySQL because of the support for sharding it gives out of the box. That's because of the commercialization, and Postgres is still catching up with it. And
There's a book of MySQL called Mariadi.
Yeah.
It's still open.
Yeah.
You can use that.
Yeah.
You're familiar with MySQL.
Yeah.
Also, you can add the executor part, right? You said you can replace the executor. So based on our system, you can customize it for our.
Yeah.
That's also.
Yes, that's so you can basically remove any part of the system and put in your own system. That is how things like CitusDB Redshift are implemented. CitusDB is a column-oriented store designed for analytics, right? But this is a row-oriented store designed for transaction processing. So, so either you should start rewriting all the parsing, stage, utilities, etc., to come up with your own column-oriented database, or remove that layer alone and put in your own layer and get things up and running.
Didn't Postgres have some NoSQL features added?
Yes, in the version I think from 9.x, JSON was added, and I would say a recently binary support for JSON was added as well, BSON, which MongoDB uses. And it's interesting to see that even with all those transaction guarantees, there's a benchmark that says that it beats MongoDB by multiple factors.
MongoDB is like Snapchat for database.
Yeah, so it can't guarantee durability because it never writes to disk in that timeline. It basically keeps everything in memory and flushes. But you can't tune that option, but you can get the same features from Postgres by increasing your checkpoint time a bit. But you can also configure that in a way that it is a bulletproof transaction system as well. Meaning, if a transaction is committed, it's visible to all.
When it comes to memory, it's kind of problematic, right? Because you said multiple updates. It will keep multiple versions in memory, waiting for a commit. So it might overload the memory.
Yeah. So the way you configure Postgres is you will give buffer size, shared buffer size. Let's say I'm going to give that as 2 GB. If the query is going to take more than 2 GB, it's going to, that is where checkpointing comes in, right? Let's say my checkpoint size is 16 MB. It is frequently very low because if you do frequent checkpoints, you can replay the log much faster when you do recovery. So for every 16 MB of change I have, I'm going to write that to disk, which means even if your query is going to update a billion row table, it's going to do a lot of checkpointing, and that's going to save the memory. But if you increase the checkpoint beyond the shared buffer size, it's going to swap out to disk, which will be slow. So careful consideration need to be put in before configuring Postgres. That's it, Jim. Thank you.
One more.
kind of rollback mechanism is given?
Okay. So if you look at the MVCC thing we did, right? You do a Xmin and Xmax, and that is visible only when the transaction is committed. If it is not going to be committed, and if there's an error before that, that bunch of changes the transaction has made is going to be another idle branch of the data. You can think of it as a garbage branch of your Git. That when you invoke vacuum, that is when it's going to identify that, oh, these things need to be garbage collected, and it's going to be removed. So there is this thing called commit log, which holds the list of all transactions being committed. This will be matched when you do a vacuum and then remove it.
But we have already committed a transaction, but you want to roll back.
It's not possible. When you commit, it's visible to others. So the idea of commit is when you commit a transaction, you confirm the changes, and that's going to be available for others. Thanks a lot.
Thank you, Varda. So this link has a feedback form, so you can submit feedback for all the 3 speakers and for the organizers.
Dinner has been arranged in the cafeteria.